Hello everyone, good evening and welcome to another day of the December Daily Challenges. This is the fourth day, day 4. If you've been sticking around for so long, then I'm sure you've been enjoying dynamic programming. Why dynamic programming? Because that is the theme of this time's December Daily Challenges. What actually happens is that every day for the last 4 days, including today, we have released a particular problem at 6 p.m. sharp. It started on 7th December and now we are at 10th December right now, and the solution for the same will be released at 9 p.m. which is exactly what is happening right now. The solution is being released at 9 p.m. The first to crack the challenge is on top of the leaderboard, and this really is ideal for anybody who's preparing for product-based companies. So you can just go and click on this link above, and once you click on that link, this is the page that opens up for you where you can go ahead and sign up free of cost. There's no cost to this. We just want you to understand how it is to face the most difficult questions of dynamic programming, and that's exactly what we have kept this test on, or these daily challenges on. And I know a lot of people tell me, well sir, dynamic programming, I think by now you might have also started receiving some memes, for example, like this one, when my friend tries to explain me dynamic programming, it's too complicated, etc. Well, that's exactly the theme of these daily challenges, that we don't want it to seem like it's some black magic or it's some very difficult thing. In fact, if you look at the last 3 questions, we've tried our best to explain it in a very concise, very simple and easy to understand manner, such that if you can think about the problem a little bit, then the solution will seem very intuitive to you. That's exactly what we have tried to show you. Now, if you want to get into further about this and learn more, you can join our algorithms and data structures course. In this, we show you how you can level up and crack product-based companies. We have more than 300 questions on all of the previously asked topics and questions of product companies, monthly sessions, assessments, hackathons, you name it. I'm your instructor over there. And yes, dynamic programming is covered over there. So we've done a couple of videos on those as well before. You can go ahead and check it out on our YouTube channel. If you like our videos, do like this video and subscribe to this channel as well. Today, I'm going to be going to the day 4 of the December Daily Challenges, which is completely free. Again, I want to say algorithms data structures is a paid bootcamp, but that is completely free and you can go ahead and test it out. Today is day 4. We have this question called grid coloring, and I'll open this up on the Edyst platform to show you how to actually approach this particular problem. So I'm just opening it up. This is where it is. So yeah, let's go. This is a question called grid coloring. There is a grid which has 2 rows and n columns, right? Something like this, 2 rows, and like this has about 4 columns, but it's saying typically n columns will be there. You will have to fill each cell of the grid with either white or black color, exactly like how this is. Some white or black color is there. 2 cells in a grid are friends if they share a side and have the same color. Okay. 2 cells X and Y belong to the same component if they are friends, or if there is a friend of X that belongs to the same component with Y. What this is basically trying to say here is that if you look at this case, we have about 6 components. How 6 components? Well, see, this white and this white are not connected by a side. Ideally, they should be connected by a side. This white and this white both are connected by a side, and hence they form one component. So this white is one component on its own, black is one component of its own, this black is one component on its own, this white is one component on its own. These 2 cells form one component, these 2 black cells form one component. So now the question is not given a grid, can you find out how many components there are? That would have been a super simple question. I wish that those are the kind of questions that were asked. That's not the question. The question is more specifically, okay, so this is just an explanation, by the way, that A, B, C and D are 4 separate components, then E, G and F, H are single components in themselves. Hence we have 6 components over here. Now the question is even more specific. It says, okay, if I tell you that you have actually n columns possible, so the input will be given to as n and k, and the thing is you'll be given n as the number of columns in this question, and k is the desired number of components, right? So you're saying that with n, can you give me exactly k components, and how many such ways are there in which we have exactly k components, right? So whenever you have this thing of like counting, right, the recursion comes into play. That is, you will need to do some recursion, which you could have also experienced in, let's say, day 2's, and even not day 1, but day 2's question could have also been solved by recursion. We did it in a better way using dynamic programming. But here basically what they're saying is, try out any combination you want. What we want to do is color them finally in such a way that given n columns, how many ways are there that we can have exactly k components? Okay. So now whenever you have such a problem, it starts becoming tricky. Like, oh, I could just color it like this, like that, like this, like that. You know, you start feeling what's going to happen there. Even before looking at the constraints, looking at the input, etc., you start thinking about how is the coloring even happening and how to even solve such a question, right? So let's go back to the slides and start thinking a little bit. Right? How will I actually go about solving this, right? So we'll be given some n columns. We need to find the valid configurations which have exactly k components. That's what we want to do. Okay. Right. So where do we even begin? Should we start coloring a little bit and see a pattern? Should we, look at something else? So in such a question, what you should always remember is try to find a relation between one state and another state. So like if you have n columns, right? What if I had just one column? And from that one column, if I'm trying to grow to the second column, what actually happens in this transition? If you start thinking about what's happening in those transitions, you will be better suited on how to do this one. Now, it could have been just a simple 2D arrays question, in which case the pattern would have been very obvious to you the moment you read it. But in this particular case, the pattern is not super obvious to us, right? Because we are trying to figure out all the possible configurations. We are not just trying to see that is this configuration possible or is that configuration possible. We are trying to see all the possible configurations under a particular constraint. That is, there have to be k components. So whenever you have to enumerate a number of combinations, whenever you have to figure out what are all the valid ones, then generally backtracking or recursion comes in, which means that you're going to generate all of the possible combinations, right? That's what you're going to try to do. And if you're going to try to generate all of them, what you need to be able to do is from one state, how can I go to another state? Okay, what does this mean? Let's take an example, right? So if you look at this example here, right? Let's say you have these this 6 as is given to us, right? The next one, the 7th, sorry, we have 6 components here with 4 columns. In the 5th column, what do I have to do here? Like, what is, depending on this state, how are the number of states increasing, right? And let's have a look. We'll come to a very big observation here, which is this observation, but we'll come to that. So for example, if let's say I color both of them white, okay, so I color this one white and I color this one white, then what I notice is, because this was white and this was black, this will be part of the same component. Like these 3 cells will be all part of the same component, but this black will be a different one. So actually, even now we have totally 6 components only. 1, 2, 3, 4, 5 with all of them, and 6, because these 2 share a horizontal side, right? They share this one. Okay. If this was covered, both are covered white. Let's say if this was colored black. Again, we have 6 components because this just extended the previous one. So we again have 6 components only. We don't have another component. Let's say if this was covered completely black. Again, we have 6 components because we got this one elongated. So this is 1 component, 2 component, 3, 4, 5, 6 components. If this was black and this was white, right? If this was black and this was white, in that case, we got 2 new components, right? So this was 6 till here, we got 7, and then we got 8. One observation that you'll make, and I want you all to take a pen, paper and try to do this yourself, is that the next column, even like, for example, now if I try to insert a next column on the right side, so let's say insert column to the right over here, right? And yeah, initially we don't know their colors. The color, what color I choose here will add or remove more components only depending on the previous column. So here till here we got 6 components. This is, and including this we got 8. The new one will only be affected. Let's say we have 8 components beforehand. The new column is affected only based on the previous column. Like if I choose white and white or black and black, it only depends on this column. Whatever happened here is prehistory. I have no issue with that, right? Nobody cares about that anymore. There are certain columns that have been reached, there are certain components that have been reached here, but only based on this one will this the coloring of the new column decide whether a new component has been added or not added, right? So that's what's going to happen over there. Similarly, in our previous case as well, dependent on this column was what was deciding whether a new component is being added or not added, right? And how does that exactly work? Well, we have multiple cases. Let's say the initial column is 0, 0. I'll use 0 for white and 1 for black over here. So let's say the initial column is like 0, 0. Then if we add another one which is 0 0, which is we add, let's say, another one which is white white, then we don't get an addition of any new component. It's the same component that's continuing, right? Whereas if I had got something like 0 1 and if I had added something like 1 0, right, now two new components got added. One was like because these two don't share anything and these two don't share anything, so 1 2 3 4, two new components got added. Initially we had two components and now two new components got added. Had it been something like 0 0 and I added 1 0, then only one new component got added. Earlier we had one component and this one is adding one more component. So depending on my previous column state, I can figure out that, okay, if my previous column was this much and we had these many components, the new column adding in will add so many components, right? That is what is going to happen. Let's formalize that a little bit, right? So what I'm going to do is I'm going to create like, let's say how many possibilities we will have. We'll have roughly 16 possibilities here, right? So why 16 possibilities? Well, it's going to look like this, right? Initially, let's say initially you had something like 0 0, right? Then if you add something like 0 1, if you add another 0 0, what happens? That is, one column is 0 0, the other column is also 0 0, then what happens? Then one column is 0 0, another column is 0 1, what happens? And this will take the form of binary numbers and will keep going on. It will become like 0 0 1 0, then 0 0 1 1, 0 1 0 0, 0 1 0 1. Okay, yeah, and yeah, I mean, so we'll have basically like 1 2 3 4 5 6 6. So far we got 6. Yeah, 6, and then we got like 0 1 1 0, and then you got 0 1 1 1. So far you got like 8, and these are all in the case in which the top row is 0. So that's white, and the bottom row is alternating between 0 and white and black, right? So then you will have like, you know, another 8 over here. 1 2 3 4 5 6 7 8. Yeah, we have 8 over here, and then these will again like repeat, right? So you have like 1 0 0 0 0, and yeah, these keep repeating like this. That's how binary numbers work, right? 0 0 1, you got like 0 1 0, 0 1 1, you got 1 1 0 0. Important to note that these are not actually numbers, we are using them to denote our states, right? All the way up to 15. So 0 to 15, we have 16 possible states. Okay, and what does that mean? So let's say, for example, this is just the first, like what the first two bits is 0 0 are talking about. I'm coloring the first, and while I'm saying this, please like take a notebook and note down, like, you know, color it white and black if you need to. So in the first case, what's happening is both are white. Okay, and if we add two more white, then what happens? The same components as previous one, that is 0 new components got added. Here one more component got added, here also one more component got added, here also one more component got added, right? The way to look at this, like for example 0 0 to 1 1, the way to look at it is, you had something like this. Let's just take this over here. Yeah, so you had something like this, obviously just one over here. So give me 1 second, I'll just illustrate this for you so that you don't get scared of dynamic programming like many people do. 1 second. Yeah, so from 0 0 to 1 0 means that you had 0 0 white white, and then this one becomes black, right? So you had 1 2 3. So these are like, this is one component here and this is another component. So another component got added if you chose to do this as 1 0, right? And similarly, if you had chose to do this as 1 1, again one more component got added, right? So similarly we'll continue for 0 1. If we add 0 0, no new components are added. For 0 1, if you add 0 1, again no new components are added. Why is that? See, if I do 0 1, right, if I do 0 1, this is what 0 1 looks like, right? To 0 1, if I add another 0 1, no new components are added. If there were two components earlier, it will continue to remain two components. Okay, for 0 1 1 0, so 0 1 1 0, two new components got added. 0 1, and imagine this was black and white, so two new components got added. 0 1 1 1, no new components got added. 1 0 and 0 0, if you're doing 1 0 1 0 and 0 0, no new components got added. 1 0 and 0 1, two new components got added. 1 0 1 0, 0 components got added. 1 0 1 1, 0 components got added. 1 1 0 0, 1 component got added. That reminds me, have we taken, yeah, okay. And 1 1 0 1, 1 1 and 0 1, so one component did get added. We got triple 1 and 0, sorry 1 1 and then 1 0, so one component got added here, and here 0 components got added. I'll just double check this, and if you feel I made a mistake, let me know. Yup, looks good to me so far. And yeah, looks good enough right now. So basically this is how the states will change when I go from one column to another column. So now the entire point has to become that, okay, start with all of the possible columns that you can get, right? So in the start, like when I have only one column, what will I do is I'll start it with 0 0 1 0 1 1 0 0. Like I'll start with the four possibilities I have: 0 0 0 1 1 0 1 1. I'll keep that in my first column, right? So this is what I'm going to do. I'm going to keep that in my first column, and then based on that I will get certain number of components. I will add the next column, and the next column will have certain number of components plus the previous number of components, and we'll keep doing this till we reach the last column. If we are reaching the last column with the exact number of components that we desire, in that case we have reached it. Otherwise, we have not got it, right? I'll explain that to you guys, don't worry. But basically what we're going to do is for each index, try a set of next columns, right? So for each index, what I'm going to do is I'm going to try a different set of next columns, and I'll also store the previous components, right? And modify the previous set of or rather and increase count of new columns, not new columns, sorry, new components. So and increase the count of the new components by changing things around, right? And once we reach, and that's the base case, finally once we reach the nth column, then at that point check if the component is equal to k. If it's equal to k, then we are done, right? Okay, so let's come back. Let's see, I know this may not have been super clear, but just follow along. The code, this is one of those questions in which the code will look more clear once we actually do it. So let me open it. I'll just remove this. Now we have not even discussed dynamic programming here, and I'll show you how this question employs dynamic programming in a bit. So we have to take input n comma k is equal to list map int input dot split. So I took n comma k, right? And the entire idea is we have to get to the nth column with k components, right? Okay, great. So we want to do that. One thing that will be good for us to note is these next states, next underscore state. It will be good to know these next states, which is basically if I know my current state and I'm moving to a different state, then how many more elements are going to be added. And now while I've done this question earlier, I don't want to again write all of those things. This is exactly the same thing as we've done in the slides. So I'm just going to very quickly paste that here. These are the next states. This is exactly what we did. If we had something like 0 0 and the 0 0, then one more component is added. 0 0 and 0 1, sorry, with 0 0 and 0 0, only 0 more components are added. 0 0 and 0 1, one more component is added. 0 0 1 0, one more component is added, and so on. We already just saw this. I'll keep this as a global variable. What I'm seeing right now over here is something called a tuple, right? It's a tuple, a tuple, and this over here is a value because this is a dictionary. So I'm basically storing a tuple. Is in Python it's hashable, so I can actually store tuples as a key, and the value can be this. You could do multiple other things. You could actually just simply do a 2D array, right? And the 2D array will also work out for you. You don't really specifically need to do this one. This is also fine. You could just a 2D array with 5 columns, with the 5th column storing the new state number and the first 4 columns storing the states. So that's also fine. You don't need to do this. I just had the Python, that's why I'm doing it. You could do it in in another 2D list as well. Anyway, so we got this n comma k is equal to list map input dot split. That is, you're taking the inputs. Now what we're going to do is define a function, a recursive function, which is basically count valid, right? So we're just going to count how many valid ones we'll have. We'll see how many previous components we had, the number of previous components we had. After we've got the number of previous components, not after we've got, we'll basically our next number or the next state depends on how many previous components we had. What was the previous top row? What was the previous bottom row? Right? What was the previous top row? What was the previous bottom row? What is the current index right now? Right? And what is k and what is n? Right? So that we have already what is k and what is n over here. Okay. All right. So we're going to count these number of valids, and obviously we always start with the base case, but I'll refer to the base case at the end. We'll just do a recursive case for now. What was the recursive case? Well, what we want to do is we want to add a new index, right? So basically I want to go further into the next index, whatever is the previous components, right? Plus some amount will come, because depending on the new column, this will change. Like whatever was the previous, if I had only 0 components earlier, right? And the previous column was 0, 0, then adding 0, 0 will not really change the components. Like this will change the components, but it will add to the number of previous components is what I'm trying to say. So depending on how many previous components were there, we add some more components, and that more is something we need to rely on for this by using these states, right? So we'll add some more. The previous top and the previous bottom are actually now in the next case we have to add a new particular number of elements, right? That is, we have to try out some more columns. What does that mean? That means I have to try out 0, 0 over here, I have to try out 0, 1, I have to try out 1, 0, 1, 1, and so on. Let me put that in a loop. So let me call this as top, let me call this as bottom, right? And I'm going to try out different values of top. So for top in 0, 1, and for bottom in 0, 1, right? So I'm going to try out both these values, and depending on that top and bottom, we'll get this, right? Then it's the next index, that's index plus 1, and k and n remain the same. We could just use a global variable for them as well. I mean, we don't really need that. So anyway, in case this, and yeah, we should define this function, by the way, above our main. So our main is this, we should define it here. Okay, yeah. So we want to do this. We want to go further, and this is a recursive thing. So for top in this, for bottom in this, we're going to go further, and this is what the valid ones will be. How many ever valid ones are there, we are going to add them to our particular answer. Answer is equal to answer plus whatever it is. So our answer initially has to be 0. At this point the answer is 0. Further on, how many ever valids are there, let's count them, and then we'll return this answer back, right? So we're going to return this answer over here. So now it's taking some shape, though there are some things that are left still open. So for example, we're going to try for the new column 0, 1 and 0, 1. So basically we're going to try all the combinations 0, 0, 0, 1, 1, 0, 1, 1. We're going to try all these 4 combinations. But depending on what the previous state was, we will be able to decide how many more elements were there. So to get the more elements, what you need to do is more is equal to, we take the next state, we refer to the next state, right? We take the previous top and previous bottom, right? Previous bottom, and we take the new top and new top and bottom, right? And this should not be a round bracket, this should be a square bracket, right? Yeah. And a round bracket as well. So now what it's going to do is, if let's say this is 0, 0, 1, 1, it's going to go here to 0, 0, 1, 1, right, and get 1 over here, right, and so on. So it's just going to keep trying to get for the different configurations, it's trying to get going to try to get what is the next how many more components are going to be added because of this, and that's going to be added over here. Okay, so that many more components have been added because of this new combination over here, right? Okay, great. So this happened. Let's say we now reach the nth index. So if index is equal to k, is equal to n, that means I've reached the nth index, right? And when I reach the nth index, I've also counted all of the possibilities from the nth index as well, right? That's one thing to note, because whenever I reach an index, I always find out all of the possibilities till that particular index, and I want to find out now going forward how many there will be. So if index equal to n, I've reached this index. What I need to check is if previous components, that is including this one, if previous components is equal to k, right? This means that this is a valid amount, or there's a valid configuration, so I'll return 1 for it. Otherwise, else I'm just gonna return 0, right? And say, okay, you reached n, you got through some configurations, you got to a particular level, but you didn't really, reach it. I mean, you got to a level, but you didn't reach k components. So just return 0. This is a configuration that you came up with, but it didn't have k components that was required. So hence mark it as 0. Okay, so that happened. So we got return 0 over here, and the answer is equal to and then we start calculating the answers. So in this case, what's going to happen is it's going to keep going further and further and further with each combination. It's going to keep going further till it reaches some nth index. It will return 1 plus 1 plus 1. It will keep coming back. Finally, it will add to this answer and will return this answer. Okay, all right. So this happened here. We've still not initiated this function, so we need to start this function somewhere, right? So that will start here. We'll say answer is equal to count valid, right? Initially, let's say we are going to start with 4 possible states, right? Because our initial state could also be 4 possible states. So what is the signature of this? We have a previous components, top, bottom, index plus 1, k and n, right? In each case, the number of components initially we begin with are different. So for example, if I began with 0, 0, then I have 1 component, right? And index will be obviously 2, k and n. That's the index that's going to be for the same for everyone. We have index as 2 because, index as 1. That is, we are on this particular index right now and we want to go to the next index, right? So that's what we are telling it. So anyway, I will start with index 1 here, and then we'll go plus. So this is in the case of 0, 0, we have 1 component. Okay, then what we want to do is count valid. In the case of 1, 1, so 1 second, 1, 1, we again have 1 component. We have only 1 component in the case of 1, 1, right? And we want to try out a bunch of other things. So what we're going to say is go to the next index, k and n, or rather the current index is 1, k and n. That has to be passed anyways, right? This should be count valid. Okay, great. Let's say we started with 1, 0, so plus count underscore valid. Had we started with 1, 0, in that case we would have 2 components. If we started with 1, 0, right? 1 k n, right? Again, 1 k n will be constant because that's the next index. And then finally, if we had started with 0, 1, right? Again, we would have had 2 components, 0, 1, right? 1 k n. And these are really, really crucial, guys, to get these states right, to get the initial state right, to get the initial thing right, because we've sort of figured out, okay, this is how our next state is going to come up, but how to get the initial state right and how to get the final state right, those are really, really important, right? So we did this and we're going to actually print answer over here. Okay. Okay, I think for a first cut, this looks decent. Let's run it and check whether at least our test cases are passing or not, whether we have made some mistake. Okay, our initial run test case is passing. What we basically did was, so basically for 3, 4, that is, if we have 3 columns and we want exactly 4 components, there are 12 ways. That's a fun thing you could do. You could, actually take it on the side and try to find out what are these 12 components and how to get them. But these are one of those problems that computers are really good at. They can figure out these numbers. Whereas for us to visualize 12 different things, that will be, and that 12 from the n number of possibilities, that will be difficult. Anyways, so just coming back to this, what we can see is what we've done so far is we've counted the valid number of, for each initial configuration. For each initial configuration, there's already some initial components, and we're trying to guess, okay, if I did the next component, what if the next component is basically, let's say 0, 0, 0, 1, 1, 0, 1, 1, then how many more will be added? That more we figured out from these states. And yeah, they keep going. In the base case, you reach the nth column. That means you return 1 if the number of components is k. Otherwise, you return 0. Right? You can reduce this condition if you need to. But anyway, the point is we got till here. Now, one thing that I did not purposely tell you at the start is because the question says that the number of ways can be so big, you have to take a modulo. You have to print the answer modulo this, right? So we already know in the past few days that if you want to take a modulo, what you do is you just add under a modulo, or you can actually, like, for example, it should be, let's also keep that prime over here. Say prime is equal to, and this time it's a different prime number, guys. So it's a different prime number. So let's take this, right, and just say, In fact, I'm not even sure if it's a prime. I guess it's a prime. Anyway, I just call it mod for now so that we don't get confused. So mod is there, and what we're going to do is answer modulo mod plus whatever this value is modulo mod, the whole thing modulo mod, right? That's one of the modular arithmetic. A plus b modulo p is a modulo p plus b modulo p, the whole thing modulo p. And we'll return this answer also modulo mod. Doesn't hurt, right? If it was already under mod, then it will just return it under mod. So that is there. Okay, so we did this, and this answer also has to be added under modulo, by the way. But because each one of them will be under modulo anyway, I can just do this as well. You could still add it under modulo. Let's do that. Let's not be lazy. Let's add it under the modulo. Okay. And let's add it over here as well, right? So this is the case, and now we should finally print the answer. Again, it should not change any of our answer for the run test case. In case of submit, let's see whether something changes, something doesn't change. Okay, so we're passing one test case here. In the other case, it's not coming as a wrong answer, but it's coming as time limit exceeded. Okay, which brings us to the next step. So for example, we did the modulo, which is just to make sure that we don't have an answer that's too big. We got the modulo, but one thing you can clearly see is that n can go up until 500. That means you could have up to 500 columns, and for each of those 500 columns, what is the possibility that you will have? Whenever you add a new column, we are adding like 4 more possibilities every time, right? And so these 4 are, by the way, like they're increasing exponentially. You add 4 more possibilities. Each of those 4 you add 4 more possibilities. For each of those 4 you add 4 more possibilities, and so on. So it's like 4 into 4 into 4. It's continuously increasing. But one thing you will notice that's happening here is you will sometimes what you will end up reaching to is, and this is how you optimize such a question. Let's say you had something like this, right? So let's go back to our drawing board. So you had something like this, right? And you're saying, okay, you know what? You have, right, till now you have about 6 components here, right? So you had 6 components and you're trying to add another one. Well, you could also have 6 components in the case like, let's say, yeah, you could have something like this and like this, and something like, so this is, how many components do I have here? 1, 2, 3, 4, and I don't know, just assume that you had something like this over here, right? Yeah, so you had like 1, 2, 3, 4 and 5, 6 components. So this also has 6 components, this also has 6 components, correct? Let's actually make it, let's try to make it even more similar to this one. So what I'm going to do here is I'm going to say, okay, we are going to just 1 second. Yeah, let's try to do something like this. What I want to impress upon you here is that, okay, so let's say you had something like this. How many components are there? 1, 2, 3, 4, 5, 6. Okay. Now this and this are different. Just by the eye, we can see that these configurations are different. Here they are same. Here they are different. And here they are definitely different, right? So basically these middle 2 columns are different, but the last column is the same, right? So essentially what we had was, we had that till here we have 6 components, right? We have like about 6 components here so far, 6 components, and we're trying to add a new one. Similarly here we had 6 components, we're trying to add a new one, and the last column here is 0, 1, right? 1 white on top and black on below. Similarly we had 6, 0, 1, like, and we're trying to add a new one. So to this column, this and this is actually equivalent, because there were 6 columns, 6 components so far, and the latest column is 0, 1. For this one, there's not much difference between them, but we will end up recalculating it. Although the numbers you will get are finally the same, we'll still end up recalculating it. So what we should do is, if we have calculated a similar configuration before, we should not calculate it again. This is called memoization, right? Let's memoize it. What we are basically saying is, if we have already encountered such a problem before, let's just store that result instead of recomputing it again. One very simple example of memoization is like in the first day where we calculated factorial once, we don't keep calculating factorial again and again. That's exactly what we're going to do over here. Now, but how will we memoize this? Well, what you will do is, because we are saying that the previous components, previous top, previous bottom, these can repeat, and index also can repeat. Like we can have a similar, through a different route, you could come to a same sub problem again and end up recalculating it again. We'll do another thing. What we'll do is, we'll store the result before returning it. So what we're going to do here is, yeah, we'll say that, okay, let's keep a dictionary here. Let's call the dictionary DP, right? DP is equal to some dictionary. And what we're going to store is this particular configuration. And we're going to say, okay, we had this DP of, what is that configuration? Well, the current component. So we say previous underscore component, right? Basically this entire thing, previous top, previous bottom, and what else do we have? Index, k, and this is right. This is what we call the function with. Well, for this element, what we're going to say is that the answer for this one is answer modulo mod, let's say, right? So now the next time we come against something like this, we won't calculate the entire thing again. We'll just check whether, okay, do you have such a configuration with you earlier? If you already have such a configuration, then just return the answer from there. Otherwise, you can go ahead, right? So that's what we're going to do here. Let's not look at the base case, but after the base case, we'll say if this particular thing, so if this entire thing, if this in configuration, if this configuration, did we get it right? Brief components, yeah, it should be components, yeah, top, bottom, index, kn, yeah. So if this brief components in DP, that means have we ever come across this earlier? If they are there, then just return, DP of this entire thing. So don't recalculate it. So if you don't recalculate it, just return this thing. Otherwise, you go ahead with the following thing. So I'm putting a return statement here. If this is not true, then anyways, this return won't execute and we'll go down here further anyways, right? So if this thing is in DP already, then just return it. So we don't recalculate this entire thing again. So this won't really change our run as such. If we do it like this, I just click run. Yeah, so run won't change really because we just, anyways, these test cases weren't as big enough to cause us a problem. Let's submit and check. And yeah, once we submit, it does pass all of the particular test cases, and we got it passing. We didn't really have any time limit exceeded, simply because we cached or we stored the previous results over there. So that's why sometimes dynamic programming is also just called cached recursion. It's not exactly that, but sometimes it's called cached recursion as well. So just a final recap of what all we did. What we did was we basically first figured out that we are going to store for each index, try a new set of columns and increase the count of the new components. And when the number of columns is equal to n, then you check for k. And the other optimization that we did on top of this was figuring out whether we have come across this state earlier or not. And if we have come across this state earlier, then just return the same answer. That is, we store that answer. In all other cases, we are just returning, we are actually calculating and then storing that answer again. So this is heavier on space, but it doesn't cause us to actually, spend time on recalculating the same problems that we had calculated earlier. So I hope that made sense for all of you. For more such dynamic programming related things, make sure that you sign up for our December daily challenge. Tomorrow is the last day. I hope you all know that and are aware of that. And yes, if you like such videos, do like this video and subscribe to this channel. And yeah, we have the advanced algorithms and data structures bootcamp. If you find any of this interesting, do come up and sign up for that one. That's it from my side for day number 4, grid coloring. I'll see you all next time for the next challenge. All the best, everybody, and thank you all for joining us today.